Good afternoon, everyone. Welcome. Dr. Zhu Hongjian is a senior lecturer in the Department of Civil and Environmental Engineering at National University of Singapore, NUS. His research focuses is on digital concrete and low carbon concrete. All right, the floor is yours, Hongjian.
Okay, thank you, Dr. Qianye, for the very good introduction. Good afternoon and good day to all the friends and colleagues who are working on 3D concrete printing. It's my great pleasure this afternoon to deliver a presentation on the research work that I have been working with my friends, with my collaborators from Swinburne University of Technology. So the title is we want to study the effects of mortar ink characteristics on the aggregate bed 3D concrete printing. So as Dr. Qianye has introduced, I'm from the National University of Singapore. This work is a collaboration between two excellent researchers. One is my PhD student, Shi Wei. And the second collaborator is Shi Wei's co-supervisor, Professor J. Sayanjan. He is a professor and the director for Center of the Sustainable Infrastructure and the Digital Construction in Australia. This morning, I believe you have watched his wonderful presentation on the 3D concrete printing. So I will present on behalf of the team. And this is the outline for the presentation. I will first introduce the definition and the motivation on aggregate-bed 3D printing. Then follow that is the experimental program. And then I will present the results and provide some discussion based on the results we have collected. And finally is our recommendation and conclusion. First of all, let's just take a look at what is aggregate-bed 3D concrete printing. Last year or in other events, we introduced this aggregate-bed 3D printing. This is basically a large-scale powder bed 3D printing. The traditional aggregate 3D printing is that we print layer of the cement paste or cement mortar layer by layer according to the designed printing path. But this printing process does not involve coarse aggregate. So in our research, my student Shi Wei has proposed a new concept is that after we print one layer of cement paste, we spread aggregates automatically on top of the printing layer. Okay, so this is the first layer for cement paste as well as aggregates. Then after aggregates is spreaded, we print a second layer of cement paste so that coarse aggregate can be bounded by the top and bottom cement paste. Then after that, we can spread the second layer of aggregates and so on and so forth. So this way, we can successfully engage coarse aggregate in 3D concrete printing. If you want to understand more information on this technique, you can refer to our publications before. It has the previous publication have well summarized this technique. And this figure, this photo shows the printing setup for the aggregate-bed 3D printing. As you can see, everything is the same as the normal or traditional extrusion-based 3D printing. We are using a gantry type 3D printer. The only thing different is that we have aggregate bed. So this is the reason why we call it aggregate bed 3D printing. So this is the feeder. Cement paste is stored or supplied to this feeder and extruded to this nozzle according to the printing path. So these are the key components. We have the aggregate spreader. You can see the red, the white color spreader. It can make sure the aggregate spreaded on top of the cement paste is smooth and that it can be leveling to the required standards. And we have this paste feeder. Okay, this is the paste feeder. Our previous work, I will just summarize briefly what we have achieved. The main benefits of this printing technique is that we can successfully include 40% of coarse aggregate by volume of the finally printed product. So this is a very impressive result. If we can include coarse aggregate in the printed products, it has a higher elastic modulus, and it also have lower drying shrinkage or autogeneous shrinkage, because aggregates will not shrink. It is cement paste that will shrink. So these are the benefits and the biggest motivation why we want to develop this aggregate bed 3D printing. However, based on our previous work, we have some limitations. The number one limitation is that we only print cement paste from the feeder to the nozzle to the aggregate bed. So this is the number one limitation. Secondly, we haven't really, in our previous work, we only investigate on one specific cement paste as the ink. So there are many other factors that may affect the 3D printed aggregates performance, such as the viscosity, the water to cement ratio. If we want to include sand, how the sand will affect the printed product. So today I want to mainly discuss a few parameters. First of all, we, instead of just using the cement paste as the ink, we are trying to use sand in the print ink so that we can printing mortar into the coarse aggregate bed. This is the number one innovation for this study. The second thing is that if we include sand, the percentage of the sand or the water to cement ratio or the addition of chemical admixtures, how they can affect the plastic viscosity. So we are going to evaluate the influence of the different mixed proportion on the printed product's performance. And thirdly, we're also trying to study the microstructure analysis. Mainly, we are going to study how the air, or especially the big air voids, are distributed spatially on the printed products. The last thing is that we are trying to see what is the correlation between the air void volume fraction and the printed product's compressive strength. So this is the outline and the main scope of this presentation. So the materials we are using in this study includes the coarse aggregate bed. The coarse aggregate we are currently used in this study has a maximum diameter of 7 millimeter, as shown in this figure. While aggregate is spread on the bed layer by layer, and we are trying to print cement mortar onto the bed so that the cement mortar can flow into the voids between the aggregates. So the cement mortar has cement, superplasticizer, retarder, water, as well as sand. So this table summarizes our design mixed proportion. So you can see from this M1 all the way to M5, we are trying to keep the water to cement ratio same as 0.4, but we increase the sand to cement ratio. It means we increase the volume of sand from zero. Zero is not included. This zero was what we have done 1 year ago. We are trying to increase the sand to cement ratio from 0.5 all the way to 1.5. So more and more sand are included in this print mortar. M6 and M7, we are trying to keep the sand to cement ratio as 1.0, but we change the water to cement ratio from 0.4 to 0.3 and to 0.45. So we can see the difference between water to cement ratio as well as the sand volume on the printing product's performance. One thing I want to highlight is that for different mixed proportions, M1 all the way to M7, we're trying to fix the dynamic yield stress. So because in our previous study, we have spotted or identified that the dynamic yield stress is very important to govern the penetration ability of the cement paste into the aggregates. So most likely the printing performance or the performance of the printed concrete is governed by the yield stress. So we finely tuned the dosage of superplasticizer and the retarder so that all the mixed proportions have almost the same yield stress. So this through this way, we can control the printing quality. And this is our printing process. We are trying to print one layer aggregates and so we are trying to print one layer of cement mortar and then spread one layer of coarse aggregate, then print another layer of cement paste. So this is basically the printing process. As we can see on this photo, that we also use some timber as a side mold. I think one previous Dr. Zhuo earlier, he also mentioned, okay, this vertical mold is not to prevent the collapse of the printing product. It's just trying to prevent any side falling of coarse aggregates, so that the side quality can be guaranteed. So this is the okay. After printing this strip, we'll kill the specimen and until the testing age. So we are going to mainly measure the compressive stress as well as the bending stress by using the 3-point bending. And later we are going to show you the performance. So we use this viscosity, the raw meter, to determine the fresh properties of the cement ink, including the cement, the dynamic yield stress, as well as the viscosity. So the relative equations are listed here. So we are trying to use this step-down shearing protocol to test the rheology performance. And this is the mechanical strength. We have this setup with quite standard cement specimen. You can see from this graphic illustration that the aggregates is one layer. In between the aggregates is one layer of cement paste printed on the aggregates. So the compressive strength is determined by the 50mm³ specimen. The specimen is cut from the printed product. In addition to the compressive strength and the flexure strength, we also employed the a very portable and affordable flatbed desktop scanner. This is a very cost-effective method. We don't have to use the CT scanning. So we just cut the surface, so that surface is very smooth and flat, and we use the normal office scanner to scan the surface. So by this technique, we can roughly quantify the void location as well as the void volume and the size distribution. As well, but of course that from the previous speakers, you can use other CT scanning or micro CT scanning to get a very meaningful and very powerful void distribution along the 3D space. So this is the result. So as I mentioned, all the 7 design mixed proportion, even though the mixed proportion are very different, but we are trying to control the yield stress is the same, but the difference is the viscosity. So this figure, you can see that the with higher sand to cement ratio, the plastic viscosity will be higher. This is because of more solid particles in cement paste. With lower water to cement ratio, the plastic viscosity will also be increased. Okay, the same reasons, because we use less water, so the solution is less dilute, is more diluted. It's less diluted and more concentrated. Then the air void structure is very interesting. This figure shows the processed 2D view vertically, so that we can see that this dark region shows the location of the air voids. So this location of the air voids is very obvious horizontally. It indicates the position of the coarse aggregate. So and also we also quantify the distribution of the air voids vertically. So this from this figure we can say the air voids can be generally categorized as 2 groups. One is coarse air, which means the air has big voids, and this coarse air are mainly found around the locations around the coarse aggregates. Okay, means like locations somewhere like this or somewhere like this is the location or the position of the aggregates layer. And there are some fine air. Okay, the fine air is most likely found in between the filament. Okay, means that is the air with smaller diameter, but within the cement mortar printed from the nozzle. And we quantify the air void distribution. This figure shows the distribution of the air voids according to the size of the diameter. So there are some fine air voids. We quantify. We say the aggregates. The air void smaller than 0.5 millimeter. Quantify. We say this is a fine air void. While aggregate air voids, which has aggregate is diameter more than 0.5 millimeter, is coarse. Sorry, this is the coarse air void, and this is fine air void. And now this figure compares for different printing ink M1 to M7, what is the distribution of the air volume and in terms of the size. So this brown color shows the coarse air, means, and this green area or green color, it shows the volume of the fine air. Okay. We try to quantify the relationship between the coarse air volume as well as the plastic viscosity of the mortar. Generally, we can see the relationship is that with higher and higher plastic viscosity, the air volume is more and more. So this is easy understood because if we have a sticky printing ink, the air voids will be more and more because it may not be very efficient to be flowing into every void into the aggregate bed, so that there will be more and more coarse air void. Okay, because the coarse air void is only exists in the near the area, near the coarse aggregate. And then we try to find the relationship between the mortar ink strength. The mortar ink strength means the mortar. Okay, we cast the mortar and we determine the compressive strength. And then we also cut the printed concrete strength and determine the concrete strength from the printed strip. So we try to find the relationship between the two. This figure 15, it shows the relationship. Okay, the vertical one is the printed concrete strength, while the horizontal axis is the mortar strength, that is the cast mortar. So generally the trend is, if you want to get higher compressive strength of 3D printed concrete, we need a stronger or higher compressive strength for the printing ink. So that will give us a positive correlation. But there are also some outliers, let's say the M6. We believe this for these two, there's something wrong with this data. We are trying to verify the result, and hopefully we can see whether this is really because of the material property, or because of this particular mix will give us higher is the air void. So we're also trying to find a relationship between the printed concrete strength with the coarse air volume. This relationship is very obvious. It's quite easy to understand. With higher and higher air void, the compressive strength of the printed concrete will be smaller and smaller. We also believe this is due to the printing quality. With the different printing ink, the printing quality will be different. So as a result of printing quality, if we have higher volume of air void, the strength will be dropped quite significantly. So we have to control the printing ink, and then that compressive strength or quality can be controlled. This figure shows a result of the rough relationship between the printed concrete with the relationship with the influence of aggregate. Sorry, this is not. I'm sorry. This is the typo error. This is the volume of the air as well as the printing ink strength. This is the last slide I want to share, that regarding the benefits or why we want to use this aggregate 3D printing. So this shows the mixed proportion for the printed aggregates. We use the conventional concrete, for example. In a conventional concrete, maybe we can have 50% of the coarse aggregate, okay, maybe 30% of sand, while 10% or less than 10% of the water, while and maybe we use 350 kilogram of cement. If we, for most of the 3D printing studies, at this moment, we don't have a lot of coarse aggregate yet, even though we appreciate the outstanding work from different researchers. They are trying to incorporate coarse aggregate in the 3D printing concrete. Even with the coarse aggregate, we do a study to compare. The cement used in those studies is about 770 kilogram per cubic meter. But for this study, our results shows because 40% of the volume of the printed product is coarse aggregate. So if we vary the printing ink, let's say we include coarse fine sand, we use more and more sand, the cement paste, the cement usage in the concrete can be reduced to as low as 575 kilogram per cubic meter. I know this is still higher compared to normal concrete, but already this is a great progress already. So that's why we want to highlight the benefits of using the aggregates into the 3D printing technique. So this is the conclusion. I want to jump the conclusion because most of the conclusions has been elaborated into the my result analysis. So I want to just maybe one or two slides on this current study or future study. Even we use the coarse aggregate, whether it's the extrusion method or aggregate-based 3D printing, the usage of cement is still very high. So what we are trying to do in my university is that we are trying to optimize or trying to lower the usage of cement, ordinary Portland cement, so that the cement clinker usage can be reduced. Let's take a look at what we are doing currently. So we're trying to develop low carbon 3D concrete printing. The innovation comes from the binder development. If we can develop low carbon binder and we use this low carbon binder into 3D concrete printing, of course, for a 1 cubic meter concrete, the usage of ordinary Portland cement can be reduced. In another word, the embodied carbon in the 3D concrete printing is reduced. So this is the media report which features our study on the low carbon concrete development by using locally available waste clay. So this is a short video. I want to play it so that we can take a look at.
National University of Singapore researchers have come up with a new type of concrete that's greener and stronger. It's made with waste marine clay, a material generated from excavation and construction works. Such materials are usually thrown away, but the scientists have found new ways to use it. The clay can replace up to half the amount of sand typically needed to produce concrete. This reduces the need for sand, which can be a scarce resource. The researchers also found the marine clay concrete to be 3 times more durable than normal concrete. They say the new concrete measures up to existing performance requirements. The scientists are working with soil-built construction to pilot the material in an upcoming project.
Yeah, so because nowadays everyone is talking about low carbon and climate change, so built environment is no exception. In Singapore, the public agency as well as the higher learning institute, we are trying the best to develop low carbon binders so that in our research university, we are trying to use locally available materials. Singapore does not produce any cement, so all the cement are imported either from Japan or from Thailand or from Malaysia. So the only resource we have, okay, whether we can use the marine clay, which is abundant in the country. So that is the research question. So that's why we are doing along this research direction. Okay, that is what we are doing currently. I thank you a lot for your listening. I want to acknowledge my research collaborators from Swinburne University of Technology. I also want to appreciate the funding support from the Singapore's Ministry of Education as well as the DGC Corporation.